sorted out. So anyway, so I'm going to present today the characterization of carbon nanomaterials using Raman Spectroscopy. So first of all, I would like to present some of my work, which we have been doing here for quite a long time. So I just wanted to give some introduction what we have been doing here. As Professor Sudhir has mentioned about my work, like what I have been working on, particularly like bio-based material. So as we are aware, like most of the polymer the most of the polymer we got like today, like in industry is being used, all those are coming from like petroleum-based polymer. So, and we know that there are some limited resource for petroleum-based polymer, and also there are some environmental concern regarding that polymer too. So, so like here in United States right now is big concern about the environment and sustainability of polymer material or any you know, that kind of research. So what we are basically doing, taking the biomass, we have like abundant biomass in nature, and try to convert them a usable chemical, and finally convert them in polymer, different kind of usable polymer. So if you look at here, for example, take any biomass, and we can extract like different polymer like cellulose, hemicellulose, lignin, starch, chitin, and terpene or vegetable oil, and then finally we could change them to further different polymer like hexose, pentose, and those could be used for like to make some the polymer. So basically we are taking like biomass, extracted chemicals, and converting them to polymer. So for example, one project we are working here, this is like a very recent project, this project was granted by DoD, Department of Defense, and in this project we are trying to make in 1970, like the NASA developed a polymer called the PMR15, which is like kind of polyamide. The polyamide, a kind of thermoset polymer. So let me like give a little bit example, a little bit like a you know, explanation what is the thermoset polymer and what is the thermoplastic polymer. So usually if you look at around, if you see any polymer, like if you take any polymer, if you are able to like melt them and mold in different different shape, so that's the kind of thermoplastic polymer. But the thermoset polymer, when you take them and you make a particular structure, you won't be able to change that structure, and it just got set on that structure. Like suppose if you make any part, like your car part, or like in aerospace, or any kind of high performance polymer, like high performance material, if you require some applications. So if you mold a part, you won't be able to change it like in different shapes. So that's the thermoset polymer. So in rocket nozzle, they use this thermoset polymer, particularly PMR15, because this polymer can sustain at very high temperature, like it can go like 300 C to 400, 500 C. So so basically what is the they take the three ingredient there, like nanic anhydride and MDA, the diamine, and then an anhydride, and mix them and make the pre-polymer, and then further cross-link them to PMR15. That's called PMR15 polymer. But the problem with this process, when they use this MDA amine, this is highly carcinogen. So it's health concern and the environmental concern too. So now, like here, the Department of Defense are looking for some other alternative for this material. So we got a project to develop some material which can replace this MDA and have the same kind of performance what we have with this MDA. So we developed several different kind of amine material, and file a patent which is pending right now, and like you can see here, some of these materials, some of these amine were like completely 100% bio-based, like all the carbon coming from the bio-base. So and some of them, like you get like 80 to 90% carbons coming from the bio-based, bio-derived materials. And here, another project we are working where we are developing epoxy polymer, like taking from some plant-based chemical and converting them to epoxy material. And like you can see here, this structure is resveratrol. That's kind of, we develop a tri-epoxy material, which is very high performance material. You can see here we were able to get like 146 degree TG for this particular material. And recently, you might remember, like in India, there was one incident in Andhra where styrene was exploded outside, and there was 12 people killed. So styrene is, like you can see here, like a styrene is kind of very toxic chemical, and it's not good for environment as well as human being. So we have a project where we are developing the alternative of styrene, because most of the like 40% the polyester thermoset polymer, they use the styrene material there. So we are looking different derivatives of, like the chemical from mint and some other like bio-based chemical, bio-based phenol, and converting them to acrylate or methacrylate and blending with like replacing the styrene material. So this one also, we had just filed the provisional patent for this material. And
okay, sir, excuse me.
Sorry.
Hello, sir, excuse me. Please make your presentation in full screen mode.
It's not full?
It is
I'm sorry.
visible. It is clearly visible to all the audience now.
Now?
Yes, sir.
Visible?
Now it is okay. Now
I'm sorry, yeah.
If you increase the percentage of visibility in screen, then it is better. Okay, sir.
Now it's visible?
Yes, sir. Now it is visible.
Okay. So this is another kind of material called like a bio-based the polybenzoxazine. This is also a thermoset polymer where you take the amine, formaldehyde, and any kind of alcohol. You can make a monomer, and then further, if you cross-link at the higher temperature, you will get a thermoset polymer. So we have also developed different kind of monomer using all the bio-based material, and we have also filed the patent for this particular material. And the last one here, I would like to talk about the biorubber. So we all aware about the soybean oil. So the soybean oil, we took the soybean oil and do some chemical modification in order to incorporate in epoxy, and we were able to get use this soybean oil as a biorubber. So as some of you might be familiar with epoxy polymer is very brittle. So if you incorporate any kind of toughening agent, you just like you might be able to increase the the toughness of the material. So you can see here we were able to increase the K1C and J1C value, which is the basic measurement for the energy requirement to break any the composite material. It was enhanced like 200% to in some cases like a 2.5% enhancement there. This was pretty huge enhancement. So we already filed this patent is already granted, and there's a company in United States, I cannot state their name, but they have licensed our technology and they are started producing this material here. So now coming to the carbon nanomaterial, which is the topic of our talk. So this material, like recently, we are also started working on the carbon material, and it was also the part of my PhD work. So the carbon material, we are familiar with the graphite. If we take the graphite and just peel off one layer on the graphite, you will end up with the graphene, the single layer graphene. And if you roll up the graphene, you will get the structure, the carbon nanotube structure. So similarly, if you just take the one carbon nanotube, slice them up and open them up, you will end up like this, the graphene structure. But this is not the way graphene or carbon nanotube is being produced. This is just like correlation between structural correlation between these nanomaterial. So the carbon nanotube could be like single wall, double wall, or the multi-wall, different type of. Similarly, graphene could be single layer graphene, up to 10 layer graphene. Here in there is a Graphene Council. They have categorized like up to 10 layer of graphene could be considered as a graphene in that category. So the carbon nanotube was discovered in 1991. Like Professor Izuma from Japan, he discovered this one. It's being around for a long time here. This is used for a lot of applications. For the graphene, it was in 2010, two Professor Andre Jaim and Navasolok. They just what they did, they took a piece of graphite and stick the tape on that and then just peel off. And they repeat that to at least 100 times, and they were able to get the single layer of graphene, and they characterize this material and publish their work in Nature publication. And they were based on their finding and based on the characteristic of the graphene, they were able to they were awarded Nobel Prize in Physics in 2010. So why these materials are important? So if you look at the surface area for single layer graphene, which is very high, like 2,630 meter square, which is pretty high surface area. Even though if we are dealing with like full layer graphene, which is also 750 meter square per gram, so aspect ratio varies from typically 2. And also, like if you have a single layer graphene, you could pass, theoretically, you could pass the light 97.7% light and electron through. So it's kind of transparent also. If you look at the stiffness, the mechanical property is very high, like 1 terapascal, and then strength is also 130 gigapascal. And if you look at the chemical processability, like all the carbons are hexagonal carbons. Means like you have the 6 carbon, like kind of benzene kind of structure. So you have like alternatively single and double bond, and all the carbon are sp2 hybridized. So you have ability to functionalize that material using any kind of either polymer, monomer, or any kind of chemical on that surface. So the surface of carbon nanomaterial are tunable. So here the Raman came in because when you modify your carbon nanomaterial, how you going to characterize? Because the Raman is the only tool where you could use to characterize, like the functionalization of carbon nanotube or functionalization of graphene, even the exfoliation of graphene and carbon the carbon nanotube also. So the Raman is like, kind of analytical tool, and is well suited for characterization of carbon nanomaterial, and it's also a vibrational spectroscopy, and is very sensitive. If you're doing any change, any modification on the surface of graphene and CNT, you would be able to detect using these techniques. You would be able to get the information like what is happening on the surface of the material. So I'm not going to talk about the fundamentals behind this one, because I'm just going to talk about how you interpret the data. If you get if you have material and you characterize them, what information you are getting from those data. So for example, if you look at here, this is the Raman spectra for single wall carbon nanotube, and then double wall carbon nanotube, and multi-wall carbon nanotube. So if you look at particularly, I'm focusing the 2 peak here is called the G peak and then D peak. D peak is kind of related to the defects. If you are creating any defects on the surface of carbon nanotube, the D peaks increase. Like all the carbon nanotube, all the carbon atoms in a carbon nanotube or graphene, they are sp2 hybridized. So if you are doing if you're changing this the hybridization, if you're changing sp2 hybridization to sp hybridization, if you're doing any kind of chemistry on the surface or doing any modification, you can see that you can easily detect that using the Raman spectroscopy. You can see that how the d peaks change in the d peaks can directly correlated with the change on the surface of the carbon and graphene materials. And also, if you look at here, this is a radio breathing mode, RBM. This is just very unique for single wall carbon nanotube. You don't see those the peaks. You can see very small hump in the double wall carbon nanotube, but at like the multi-wall carbon nanotube, there is no RBM for that one. This is actually related to diameter of the carbon nanotube. So this kind of information, and also the ratio between G and D peak can tell you like how many carbon is changing sp2 to sp3 hybridization. So next is for graphene. So if you look at the graphene, if you take the graphite and we have like here, this is the 2 peak, and we have the G peak and then also D peak. So if you have the perfect graphite seed, there is no defects on that. So you can see here there is no D peak. And if you have the perfect graphene and there's no D peak, because there's no defects on all the sp2 hybridized carbon. But that's not the case that's the kind of ideal scenario. But basically we get like whatever the material is available in the market, they have a lot of their defects, because the way they prepare this material is like they take the graphite and then they chemically exfoliate them, either chemical exfoliation or them just like use some kind of physical exfoliation also. Like it's kind of combined, like chemical, physical. There are different methods, but there are very few company right now they can produce a larger amount of graphene, because the process is kind of tedious and then expensive also, and everybody don't have that capability to produce a larger amount of graphene and keeping the consistent their production, like producing every time the same kind of purity and same kind of particle size distribution and in their product. So also you see here, this is the G peak. This is also we could simply like the intensity could be depend on like if you have the intensity change, it's also related to you can figure out like how much layer you have in your graphene if intensity changing from single layer, double layer, and triple layer. But keep in mind, this is also very dependent on the laser, what kind of laser you are using in your Raman spectra. So that's why we more focus on this the peak position change. Like if you can see if have like a higher Raman shift, you get like the single layer, and then you get like like a double layer, and then if it's completely shift like a graphitic layer. So we could use this formulation where the peak position, if you plug your peak position here on the G and number of layer, you can calculate using this simple equation. So here is few example. When if you look at this spectra here, the red line here is functionalized graphene nanoparticle. However, this is the black one is just this is just like the pure graphene nanoparticle. So you can see here we don't have the D peak is very minimal. When we functionalize, we change sp2 to sp3 hybridization, D peak is like shifting up, and D by G ratio is also changing. If you see for just the pure graphene, we have like 2.4, is triple-fold enhancement, is good 0.67%. So, and also the 2D peaks also, the shape of 2D peaks like tell us more about what kind of material we have. And when you couple with this Raman spectra with XPS, you get more information about your material. So you can see here, when we do some XPS measurement on the Raman on functionalized carbon nanotube, we were able to even quantify how much sp2 hybridized, sp3 hybridized carbon we have, and how much oxygen content, which is present in form of, you know, the CO, carbonyl, and ester kind of linkage there. So you could be, if you combine these two tools like Raman Spectra and XPS, you can get a lot of information about your material. Here also the similar story. If you can look at this Raman Spectra, we have like graphitic structure, and when we have the graphene oxide is shifted a little the higher side, and then again if you functionalize that graphene oxide and reduce them, so it's shifted back a little bit. So it's tell about you, like, you know, what kind of material you are dealing with. And further, if you do some XPS, you will get more information about how much sp2 and sp2 hybridization you have. And then the last the talk, like it was on, like, you know, the thermogrammetric analysis. So you can use the TGA also to estimate how much you know, functional group you have on the carbon material. So for example, if you look at here, if we take the graphite, there is if it's the perfect graphite, there is no any functionality and no impurity. There is no degradation on that. You just, like, if you heat it up to 800 C, there is no degradation. But if we prepare the graphene oxide, you can see here there are a lot of oxygenated group on the surface, and when you heat it up, then you can see degradation here also. And similarly, if you graft any polymer on the graphene, you can see that the degradation of graphene and those polymer also. So the same here, like the same sample, when we do like sp2 and sp3 hybridization ratio, and then what kind of carbon concentration, and then oxygen concentration and nitrogen concentration using the XPS analysis. So there's two tools, like one like Raman, another one, the XPS, is very useful in order to characterize any kind of nanomaterial, particularly carbon-based nanomaterials. Here we have another example. This is for just a carbon nanotube. I published this paper during my PhD. So you can see here, when we have the pure multi-wall carbon nanotube, you can see the D peaks and then black the G peaks. But when we functionalize that multi-wall carbon nanotube, if you incorporate any functional group, you put any polymer, you can see here like the D peak is just, you know, the ratio between D and peak is completely changed. So which is telling also the same story, like you are changing sp2 hybridization to sp3 hybridization. And you can see also that's proof through the XPS, saying that we have different composition of oxygen and nitrogen. And the TM image is also, so this is a pure carbon nanotube. When we grafted polymer, you can see like how you know, uniformly carbon nanotube was grafted on the surface of how the polymer was grafted on the carbon nanotube surface. So these tools are very useful in order to, if you want to characterize like a carbon-based material. So the conclusion of my talk would be like, you know, the Raman spectroscopy is particularly well suited for any morphological characterization on the carbon-based material. And like every bond in the Raman spectrum, you know, correspond directly to the specific vibrational frequency of the bond within molecule. So you would be able to know that, like, what kind of functionality you are putting on the surface, and how sp2 hybridization is changing to sp3 hybridization. And also vibrational frequency, and also like based on the position shift, you would be able to you know, get information regarding layer structure of the graphene materials. And if you combine this, the Raman spectroscopy with some other technique like XPS, TM, or like TEG, you could get the whole picture, like what is happening, like, you know, how your material is changing for any applications. So thank you, and if you have any question, I would be happy to answer.
Thank you, sir, for your nice talk on these polymer composites based on the nanocarbon-based material and their applications. Now, I asked the audience for the questions. There is no any questions.
Hello.
Yes, can
Hello.
you ask your questions, sir?
Yes. Yes, sir.